Okay, now let's wrap this up by solving the initial system with the initial condition y of 0 equals 3 2i minus 1. Now I've thrown a complex value in here just so we can see that this works out just fine with complex numbers. Okay, the fundamental set for our equation, we've established that this is a fundamental set. This is just our real and imaginary parts of the solution that we got to the equation for our first eigenvalue, corresponding to our first solution vector. Okay, coming from the first eigenpair, we take the real and imaginary parts and we get this fundamental set. Then our general solution, y of t, is c1 times this vector plus c2 times this vector. Not writing that out again, I'm just going to write that then y of 0 will be c1 times this vector evaluated for t equals 0 plus c2 times this vector evaluated for t equals 0. It's very clear well, I'm not going to go through why the values are what they are. It's clear that e to the 0 cosine of 0 is 1, so we're going to get c1 times 1. And that e to the 0 times sine of 0 is 0. E to the 0 is 1, sine of 0 is 0. So that we're not going to get a c2 in our first component. Plugging in zeros here, the sine of 0 is going to be 0, e to the 0 is 1, cosine of 0 is 1. We just get 1/5 times the c1, and over here we get 1/5 times 3 cosine of 0, which is going to be 3/5, and that's 3/5 of c2 when multiplied through by our constant. So that's our expression for y of 0 in terms of this fundamental set, and by our assumed initial condition, that has to equal 3 2i minus 1. Well, this leads to a set of simultaneous equations. We could write this as a matrix equation, invert the matrix, etc. Or we can simply write down the system of equations, and I'm going to choose the latter. We get c1 equals 3, which makes it fairly easy to solve for c1, and 1/5 c1 plus 3/5 c2 equals 2i minus 1. Okay, now even if we had a non-zero term here for c2, we would be able to do this solution. The manipulations be a little more complicated, but we've seen how to do the manipulations with complex numbers, and that's something you simply have to practice. In any case, plugging c1 equals 3 into this equation gives us the equation c1 is 3, so 1/5 of c1 is 3/5, and then plus 3/5 of c2, we get 2i minus 1, which means, well, that's 3/5 of c2 equals 2i minus 1 plus 3/5. That's going to give us 2i minus 2/5, so that c2 equals 5/3 of 2i minus 2/5, which equals 10/3 I minus 2/3. Once more, more generally, we're going to get C1 and some multiple of C2 when we plug back in. That's going to make the equation a little more complicated, especially if we have a complex number here. But we just keep our wits about us and solve the equations using the same algebraic steps we would ordinarily use, just doing the algebra of the complex numbers, and we would get two solutions, C1 and C2. In general, those two solutions might both be complex numbers. Now, before we go on with this solution, let's digress back to the question I posed at the end of the last clip. How could two real valued functions, because the R and the script R and the script I functions are both real valued, they have no imaginary numbers in them, how could a sum of multiples of those two real column vectors give us something like this, which has all kinds of imaginary numbers in it? And the answer is simply that when you solve for C1 and C2, both C1 and C2 will be complex numbers in this case. So remember that as soon as we move into complex values, that all our constants will in general be complex. They might end up being real, they might end up being pure imaginary, but in the general case they're going to end up being a combination of real and imaginary complex numbers. Returning to the task at hand, okay, we're trying to solve this system with this initial condition. We're using the fundamental set we got from the real and imaginary parts of our first solution coming from our first eigenpair. And we've obtained values for C1 and C2, so it remains only to write out our solution. Our solution is y of t, come down here, C1r plus C2i with the numbers C1 and C2 that we've just obtained. C1 is just 3. Our r vector, and eventually we'll get a little tired of writing this thing out, e to the 3t cosine of 3t and 1/5 e to the 3t times cosine of 3t, and I notice over here that when I look up here I forgot to close that parenthesis, that set of parentheses, minus 3 sine of 3t plus C2, which is 2i, 10/3 I minus 2/3 times our second fundamental vector, e to the 3t sine of 3t 1/5 e to the 3t times 3 cosine of 3t plus sine of 3t, close the parentheses, close the brackets. So that, having applied our initial condition to the general solution that we get from this fundamental set, evaluated the constants C1 and C2, we get our specific solution that satisfies the given initial conditions, and of course we can add these two solutions, which I'll do off camera. So again, C1 being 3, C2 being 10/3 I minus 2/3, C1 times our real part, and C2 times our imaginary part of our first solution gives us this. Distributing through here and summing everything up, I believe, and you can verify it, I'm not going to bother even checking this solution. Take it as a problem to verify, either confirm my solution or see where I went wrong. Okay, but multiplying through by 3 here, we get 3. Okay, every term has an e to the 3t, so I simply factor that out in every case. So we get 3 cosine of 3t, and here we get negative 2/3 sine of 3t, and then we get a 10/3 I times the sine of 3t. So our first component comes out in a very straightforward manner. Our second component is a little more arithmetically complicated, but not difficult at all if we simply write everything out and do it carefully. And we get 3 times our 1/5 times the cosine. That gives us a 3/5 times the cosine. And down here we get a negative 2/3 times 1/5 times 3 cosine. And I believe that gives us a negative 2/5 on this cosine, which added to the 1/5 in the cosine gives us the negative 1/5 times the cosine. And again, distributing these constants through in the second set of solutions, of which we got a second component that needed a closed parenthesis here. Closed set of parentheses. We close the set of parentheses with a parenthesis. Okay. In any case, closing the parentheses up here. Once more, you can simply write this solution out and see if you can verify. That one doesn't look great to me, but I've checked it a couple of times. I kind of think it's right. This is our general solution. To the system, y prime equals, let's see if I remember this right, 2, 5, negative 4, y, with y of 0 equal to 3, 1 minus 2i. Let's see, I got to look back. 2i minus 1. And when I say general solution, the word general doesn't belong there. It's just a solution with this initial condition.